Hey everybody, this is my blueberry plant, and he's doing okay. That one died, and so did that one. But let's focus on the positive. I got to get this soil to be acidic, and so one of the ways you do that is with some good old ammonium nitrate. Doesn't sound like an acid, does it? Ammonium is an acidic ion, and that's what we're going to talk about today. And it's clumpy and it's a mess, and it needs to rain on it, but it's soluble. And so let's go talk about acidic and basic salts, the acid and bases in disguise. Well, hi everybody. Hi, Mike here. Sorry about the downer with the blueberry plants. 66.6% mortality rate for those 2-year-olds. I know life is a fragile and delicate balance, but anyhow, we need to move. We need to push on because that's what they would have wanted. Anyhow, here's the deal, folks. Some acids and bases are sort of acids and bases in disguise. As I said earlier, you dissolve an ionic compound into water. Oh, good, back to good old Gen Chem 1, it makes ions, and then one of two things is going to happen. Either those ions are a conjugate acid or base of a strong acid or base, or they're the conjugate acid or conjugate base of a weak acid or base. And then how do you tell that? Well, you don't just read its aura and say, oh, chloride, what are you? I feel your aura is blue. No. You look in the chart and you find out that everything in here that is a negative ion on the Ka chart or is a positive ion on the Kb chart, those are conjugate acids or bases of weak acids or bases. And that's really important because the ones that aren't, the ones that are conjugate acids or bases of something strong, they do nothing. They're spectator ions. They float around in the solution, being a positive or negative, or a positive 2 or a negative 2, and they don't do anything past that. These conjugate acids and bases of something weak, however, are part of an equilibrium system, and they will establish the other thing that is its conjugate pair. So those are the things that are acidic or basic, like ammonium in my ammonium nitrate. But let's use an example first that is neutral, and let's explain why is this, all right? So think in terms of your Ka and Kb equilibrium. So we're going to take chloride. Let's just say chloride somehow magically landed into solution, which by the way it doesn't. It needs to be paired with something positive, right? But you got chloride, you dissolved it, and now it's in water. And what happens when it hits water? Well, it's part of this system. It's the conjugate base of a strong acid. That is a straight arrow situation, folks. And basically, it has no ability to go back. That's for double arrow. So once a chloride is produced by HCl, it has no ability to go back and pick up an H+ and act like a base. And so chloride is a neutral solution. If you want to use numbers, think of this. If something has a Ka of infinity because it's a strong acid or base, a strong acid in this case, then that means this equilibrium lies totally to the right. That chloride is pinned there. It can't go and change itself. It's a stable entity, and that's why it's part of a strong acid system. Let's take, for example, something that's part of a base. So you go and you take sodium ion. What acid or base is that related to? Well, it's a positive ion, and so it's related to the strong base sodium hydroxide. And when sodium hydroxide dissociates in water because it's a strong base, that sodium is stuck there on the right. This equilibrium lies completely to the right, like Kb of infinity. As a matter of fact, why don't we just write that? Something that's strong. Think of it as having a K of infinity. Kb equals infinity sign, which means this thing is completely favoring the reactant. So now let's go back. Let's go back here. Let's say, what happens when you put a sodium chloride in water? Well, basically, now that we've talked about that, sodium chloride in water, when you take sodium chloride solid and you dissolve it, you get sodium chloride aqueous, and then that breaks up into ions. And since we just introduced those two as neutral ions, you should expect a pH of 7 out of salt water, sodium chloride. So that's basically because, you know, this is tied to a strong acid system, this is tied to a strong base system. And so now we can take all the strong acids and bases that we talked about last time, and their other ion, the other ion that is not H3O plus or OH minus, that ion is going to be just like a sodium or a chloride. It is going to be neutral. So here are a list of neutral ions, and I realize the danger here, because I know students, you're going to say, I'm just going to memorize all those. And that'll work for you, but it might not work for you sometimes, because you'll say, hey, fluoride, that's a neutral ion. No, it ain't. Even though it looks like a chloride or an iodide, or actually, to be honest with you, bromide, because HBr is a strong acid as well. And so what do all these things have in common? They're part of a strong acid or base system, and they can't reverse and go act like an acid or base themselves. They have no strength. And back to Gen Chem 1, when you did spectator ions, these were all the usual suspects. Chloride, conjugate base of HCl, strong. This nitric acid, strong. It makes nitrate. Sodium hydroxide, strong. So is potassium hydroxide. So that's nothing that appears on your Ka or Kb chart. Notice, this is a different ballgame. So let's talk about ions that are not neutral next. All right, let's talk about my blueberry plant, the lone survivor. I go to a farming supply place and buy ammonium nitrate. It's a fertilizer, but it also, besides giving it nitrogen, it's acidic, and it will make your soil acidic. So why is that? I could have just put vinegar in there. I don't want to put vinegar in there. It's too expensive, and it's not concentrated. So why? All right, here we go. We've got ammonium nitrate. This is the multi-step thinking you need to do. You need to think, what's that going to do? It's going to bust into ions. You got to go back and review Gen Chem 1 if you don't know what your ions are, how they, you know, what charges they are. This is ammonium ion. This is nitrate ion. Nitrate ion is one of those neutral ions, but this guy is the conjugate acid of a weak base, ammonia. And so let's take a look. Let's point him out. There he is right there. That's ammonium ion. Double arrow. That thing cannot exist by itself. This is part of an equilibrium. As soon as that hits water, nature says you've got to establish some NH3. And so when ammonium ion, when ammonium ion hits water, it's not going to just sit there. So here's the equilibrium that it's part of that I just showed. It's on the Ka chart too. Kb is 1.8 times 10 to the minus 5. That's not 0, that's not infinity. And so this is the thing that's different from what we just got done talking about, is that is a reversible system, and you can't have just ammonium in there together. So how is it going to happen? How's that going to establish its partner, NH3? If it hits water, it's going to have to make the other component, which is NH3, aqueous. And now to balance this, how did it do it? It had to give an H plus to water, which we all know is H3O plus. Let me underline those two things. They've got to be in there together. So if you took ammonium nitrate, ammonium chloride, you now need to play this out in your mind. You go and you say, okay, ammonium ion is part of a weak acid-base system. It is the conjugate acid of something weak, which means it needs to make the conjugate base, and in doing so, just reaction with water. it will have to produce H3O plus in order to balance that reaction there. This term is called hydrolysis, which basically means reaction with water. So the things on the chart that are ions that aren't H3O plus or OH minus are ions that will undergo hydrolysis. This one happens to be acidic because it needs to cough up an H plus onto water to get the conjugate pair, which is NH3. So let's take another one. Someone says, hey, potassium fluoride, what is it? Well, here's your thinking. First, don't look down here yet. First, you go ahead and you take potassium fluoride, you break it into its respective ions. You recognize that that is part of the other product of something that is a strong base. And then you say, hey, fluoride is the conjugate base of a weak acid, hydrofluoric acid. Watch out, it looks like hydrochloric acid, but it doesn't have a K of infinity, HF. And look at, so there's F minus, there's double arrow. And so when fluoride hits water, this equilibrium dictates that it can't be there by itself. It's got to be this and that at the same time. And so now, you know, this is the thing that's in the chart. When you see this here, you have to go and say, okay, what's fluoride going to do with water? Well, it certainly can't give it an H plus. It doesn't have one. It's going to have to take an H plus from water to make HF and OH minus. So your toothpaste has fluoride in it, so does your water. Technically, that makes it slightly alkaline. And so this is an example of an alkaline ion. So, you know, to review here, anything that is a negative ion of a weak acid is going to be an alkaline ion or basic. Anything that is a positive ion of a weak base is going to be acidic. And so those are the conjugate acid bases that have some strength. And so, oh, I just realized I goofed up. Quiz time, whoop, whoop. Quiz time, whoop, whoop. Except number one is stupid because I just went over that. Well, hey, this will give you some confidence. Go ahead and figure out which of these salts are acidic, which are basic, and which are neutral. Remember, you got to take the two-step process, what ions are produced, and what category they fall in. Okay, take some time to do that now. Welcome back. Hope you did good. We'll find out. And this was silly because we talked about it. So real quick like a bunny, ammonium, conjugate acid of something weak, nitrate, conjugate base of something strong. This is acidic because it's the conjugate acid of the weak base, NH3. This is neutral because it's the ion. I don't even like calling it a conjugate base because it's really not a base. It's the ion produced by strong acid HNO3. All right, here we go. KNO2. K plus. Got to watch out, NO2 minus is not the same as NO3 minus. It's quite a bit different. This is a neutral ion as we discussed before. It's tied to the strong base KOH. This is the conjugate base of nitrous acid. Nitrous acid is HNO2. And it has a Ka of not infinity, but 4.6 times 10 to the minus 2. That, my friends, is an alkaline basic, I should say. It's a basic ion. Oh, by the way, so when you put this together, acidic plus neutral is acidic. Neutral plus basic is basic. Sodium cyanide. Ooh, don't ever eat it. Sodium, neutral. Ion produced by the strong base NaOH. Cyanide is the conjugate base of hydrocyanic acid, which is a weak acid. This is a basic ion. If you take neutral plus basic, you get basic. Potassium, we already talked about, neutral. Nitrate, we already talked about, neutral. Neutral plus neutral equals neutral. There you go. And that is just qualitatively, no numbers yet, numbers are coming just next, qualitatively determining what is acidic, basic, or neutral. And so, okay. Now let's do some number crunching, folks. Get your calculator. Get it, unholster it from your pants where you keep it in your belt. All right, I'm back and I'm unholstering. There it is. There's my calculator. And I'm going to brandish it, but only because I feel threatened, because there's a problem. And the problem is we never told you how to calculate what the pH of something is. And so here's the relationship. If you have a conjugate acid-base pair, something like fluoride ion and hydrofluoric acid, or ammonium ion and ammonia, Ka times Kb is 10 to the minus 14, always. Now, why? That's what I want to prove to you. I want to do a proof. This would be a mathematical proof. Let's say we have some acid, HA, and it's weak, and its Ka is 1 times 10 to the minus 5. Just hypothetically. I'm trying to make the numbers nice and round. So, okay, let's write the reaction of that weak acid with water, making H3O plus and A minus, and the Ka is 1 times 10 to the minus 5, we said. Let's say we had the conjugate base and we put it in water and we knew its concentration. We wanted to know its Kb. That's how we solve all these problems, right? Well, then we could write this. A minus plus H2O makes HA and OH minus. But we just don't know what its Kb is. Well, we would use this relationship. But why? I want to show you why the relationship exists. Let's add these two reactions together. Does stuff cancel? Yeah, stuff cancels, right? That cancels. This cancels. And what do you get? You get H2O liquid plus another H2O liquid goes to make H3O plus OH minus. Does that look familiar? That is Kw. That is 10 to the minus 14. And so if you know the Ka of something that's a weak acid, you actually can figure from this relationship Ka times Kb equals 10 to the minus 14. And what I'm trying to say is the fact that these two reactions added together means that that is a underlying principle of water. It's in the background at all times. No matter what you put in water, this relationship still holds true, that that's 10 to the minus 14. And now I know I need to know the Kb of the A minus, whatever that was. And so this would now be 10 to the minus 14 divided by the Ka of 1 times 10 to the minus 5. And that would be 1.0 times 10 to the minus 9. It also points something out. The stronger an acid is, the weaker its conjugate base, because this is an inverse relationship. So, you know, if you took water, you would say, you know, it's 1.0 times 10 to the minus 7, you know, something around there. So if you took, I should have said a weak acid that was 1 times 10 to the minus 7, its conjugate base would be equal strength. But if you take something like very weak, and it has a very small Ka, its conjugate base will be even, you know, more potent. And so that's what you can kind of take from this, is that as you go, this chart happens to be organized in terms of increasing or decreasing Ka, depending on which way you go. So the top of this chart has bigger Kas than the bottom. But on the bottom is where all the strong conjugate bases are because of that inverse relationship. So the stronger an acid is, the weaker its conjugate base. The weaker an acid is, the stronger its conjugate base. But that doesn't solve the problem for us. What we're going to do next is we're going to say, okay, you got, I don't know, toothpaste, something like that. We're going to solve for what is the pH of 0.1 molar sodium fluoride. So we're going to go and we're going to put sodium fluoride in water, and you got 2 steps to this kind of thinking. One, is it neutral? Because sodium fluoride's a neutral salt and both of these ions are neutral. So first step, 1. Write separate ions. So what we're going to do is we're going to say NaF aqueous, when it goes into water, it makes Na plus, which is neutral, plus F minus. Neutral, basic. Okay, the next step is 2. I'm going to write the reaction of non-neutral, so if it's acidic or basic ion, ions in water. So here we go. That's basic. Why? I'm going to go ahead and do what we did earlier. F minus aqueous plus water goes to make HF as it has to, because it's part of a weak system, plus what? OH minus. Now I'm going to go and I'm going to find the Ka, or Kb, I should say. So what we're going to do now is I'm going to look for that guy in the chart, and it's related to the weak acid HF, which has a Ka of 3.5, but this is Kb. Kb equals question mark. So I'm going to go ahead and say, okay, I need Kb. Ka times Kb equals 1 times 10 to the minus 14. From the chart, I have Ka. Kb is going to be 1.0 times 10 to the minus 14 divided by 3.5 times 10 to the minus 4. Now, hydrofluoric acid is pretty potent stuff for a weak acid. So that relatively big Ka is going to make fluoride ion kind of a wuss when it comes to its strength. But it's still something. When we get done, this ain't going to have a pH of 7. It ain't neutral. So here we go. 1.0 times 10 to the minus 14 divided by 3.5 times 10 to the minus 4. And that is 2.8, do 2 digits, 2.86 times 10 to the minus 11. Now it's just like any other problem we've done. What's the pH of something that's a base that's 0.1 molar with a Kb of that? So it's rice table time. So let's go ahead and do that. First of all, I'm going to go ahead and rewrite this equation again. F minus plus H2O goes to make HF plus OH minus. Now I know that that's its KB. So let's go ahead. I, C, E, 0.100. You're probably getting bored of this now. 0 and 0. Minus X plus X plus X. So 0.100 minus X, X and X go all up in the KB, which, by the way, for this thing, I'll write it here if I got enough. KB is concentration of HF times OH minus divided by F minus. That's what that means. And so now what I got to do is I got to put that all up in there. And so therefore X times X, so X times X divided by 0.100 minus X equals 2.86. Not the number from the chart, but the number we got indirectly from that relationship. Now, folks, whoopsie. Can I do 100 times the rule? Hell yeah, I can. 0.1 is way more than 100 times bigger than 2.86 times 10 to the minus 11. And so what we could do now is we could say that is X squared divided by 0.100. Trying to get to X, and then we got to remember what X meant. X meant the OH minus concentration. You've got to keep that in mind. It's a base, right? Oh my, look at my, oh my goodness. So, okay, here we go. X squared equals 0.1 times 2.86 times 10 to the minus 11 would be 2.86 times 10 to the minus 12. Square root time. (1.69 times 10 to the minus 6 is X, which, remember, when you set up your equation for the ICE chart, that is OH minus. If I do a negative log of 1.69 times 10 to the minus 6, that would be the POH. Let's see what I get when I get the log button. I get minus 5.77. Of course, it's minus that. POH equals 5.77. pH equals 14 minus 5.77. 8.23. So even that is a kind of a wuss of a base because of its very small KB. Once you go and calculate it, you know, 2.86 times 10 to the minus 11, that's really small. But you still have something that's basic. It doesn't take much to nudge a pH past 7. And so you'd say, oh, well, that's kind of close to 7, isn't it? Nah, it's just one digit away. No, it's still 10 times greater. If the pH of your blood became 8.23, you would experience a condition called death. And that would be not good. You'd go into, you'd be in alkalosis, and you'd be, you know, where my blueberry plants are. I'm sorry there's been so much death in this particular video as a theme. It just happened by accident. But anyhow, don't do that. Don't go to pH 8.23, but it's still, there's very, very subtle acids and bases in nature, and we need to recognize them. Okay, that's been a lot, folks. Next time, we're going to talk about why you don't die. if you were to ingest an acid or base, and it's because of buffer solutions like the one that's in your blood and governs its pH. Okay, talk about that next time. Take care. Bye.